You know, sometimes the most incredible stories aren't told in words, but in mathematics. Today, we're going to be scientific detectives. We're going to decode the story that's hidden inside one single complex signal. And our first clue? It's the blueprint itself.
And here it is. This is our blueprint. Now, at first glance, yeah, it looks like a total jumble of symbols, but I want you to think of it like a set of instructions. Instructions describing a physical event, from its explosive start to its fading finish. Our job together is to translate this mathematical language into a real-world story.
So that's the big question, right? What are we looking at here? Is this the echo of a distant star? Maybe the vibration from a medical scan? Or is it something else completely? Every single part of that equation is a clue. So let's start cracking the code.
Okay, first things first, we've got to break this equation down into its core pieces. We're going to look at each part of the puzzle one by one before we put it all back together and see the whole picture.
Right at the very heart of our signal, we've got something you might already be familiar with, a damped harmonic oscillation. That's what this R0 e to the minus lambda t sine of omega t part is all about. Just imagine striking a bell. It rings really loudly at first, right? And then the sound just, whew, fades away. That's exactly what this part of the equation is describing, a simple vibration that decays over time.
But hang on, there's a really subtle but crucial clue hidden right in plain sight. The equation uses a sine function, not a cosine. And in physics, that is never an accident. A cosine start is kind of like pulling a pendulum back and just letting it go. A sine start, though, that means the thing was sitting still and then bam, it got a sudden sharp kick of energy. Our bell wasn't just released, it was struck, and struck hard.
But that initial strike, well, that's not the whole story, not even close. The equation tells us that the first signal wasn't alone. It was actually followed by a whole series of echoes, and the math for that is surprisingly beautiful.
See this part of the equation, the one with the big sigma, the summation symbol? You can basically think of that as a recipe for reverberation. It's telling us, take that original signal, make 12 copies of it, and then for each of those copies, delay it by a certain amount of time, Tj, and give it its own starting volume, Aj. It's literally the mathematical version of shouting in a canyon and hearing your voice bounce back from all the different cliffs.
And this is where it gets really cool, because we can map those abstract terms to the real world. Every single one of those 12 echoes corresponds to a reflection from a real physical object. An echo that shows up fast, like T1, must have bounced off something nearby. An echo that takes forever to get back, like T12, had to come from the most distant target. And that amplitude, A of j, that tells us something about how big or reflective that target was.
Okay, so we have a sudden impulse, and it's 12 echoes. But there's another clue lurking in our equation, and it might be the strangest one of all. It's the term that controls how the entire signal fades away, and it's pointing to a seriously hostile environment.
What's wild is that our equation actually has two different types of decay happening at the same time. The E negative lambda t part we talked about earlier is exponential decay. You know, steady, predictable, like a hot cup of coffee cooling down. But the entire signal is also being multiplied by this other thing, a power law decay, 1 over t to the 7th. This kind of decay is totally different. Its rate actually changes over time, and you usually see it in much more complex, chaotic things, like turbulence.
This table really nails the difference. The exponential decay, that comes from the signal source itself, its own internal friction, if you will. But this power law decay, that's coming from the environment the signal is fighting its way through. And as we're about to see, this is no ordinary environment.
7. The critical clue here is the value of that exponent. It isn't 1 or 2 or 3, it's 7. And in the world of physics, trust me, a number like that is extreme. So, why is 7 so extreme? Well, think about it this way. A signal just spreading out in open space, like the sound from a speaker, it naturally fades at a rate of 1 over time squared. Our signal is fading at 1 over time to the 7th power. That is ridiculously fast. It means the medium our signal is traveling through is incredibly hostile to it, just sucking its energy away, probably through intense scattering or absorption. It's like trying to see a flashlight beam through a thick, swirling sandstorm.
So, we have all our clues now. A sharp impulse, 12 distinct echoes, and an extremely difficult medium to travel through. It's time. Let's assemble them into the complete story of what actually happened.
Here it is. This is the story our equation tells. First, some sharp impulse creates a wave.
Second, that wave immediately plows into a complex, messy environment that just drains its energy like crazy. Third, as it travels, it bounces off 12 separate objects, creating all those echoes. And finally, some kind of sensor picks up what's left of the original signal and all of its fading echoes. But wait, there's one last piece.
And that's the E of Tarn term. This is the equation's dose of reality. It's all the random, unwanted noise, the background hiss, thermal jitter, electronic interference, all the stuff that gets added to every real-world measurement. It's the difference between a perfect architectural blueprint and an actual building standing out in the real world.
And this noise, it has a huge practical consequence. Because our main signal is decaying so incredibly fast, it doesn't take long at all for it to become weaker than that background noise. And that means the echoes from the most distant targets, the ones that arrive last, are probably going to be completely buried in that static, making them pretty much impossible to even detect.
So after taking this whole thing apart, piece by piece, what is this bizarre signal model actually good for? I mean, where in the world would you even encounter something this specific and this complex?
Well, it turns out this model is perfect for any kind of system that sends out a pulse and listens for echoes in really extreme environments. Think about medical ultrasound trying to see through dense bone, or maybe sonar trying to find a shipwreck in murky, turbulent water. You could even use it for seismic surveys, trying to find oil deposits in really fractured rock. In every one of those cases, you've got a signal, you've got echoes, and you've got a medium that just eats energy for breakfast. But even with all these potential uses, the central mystery is still there. As the source material itself says, the biggest question is, why 1 over t to the 7th? What physical process, or maybe what combination of processes, could possibly lead to such a specific and extreme rate of decay? Answering that question, well, that's where the next wave of research is headed. And that just leaves us with a final thought. This one single equation told us a surprisingly detailed story about a very specific event. It really makes you wonder, how many other stories are out there, hidden in the noise all around us, just waiting for the right person to come along and finally decipher their mathematical blueprint? Thanks for joining me.